so let's talk about SQL, SQL, Structured Query Language. So SQL was an attempt to bring down the bar for humans, regular human beings, to be able to interact with large data sets. So in a way that would look like an English language, pseudo-English conversation with a database. Now it's a little quaint, trying to sound like an English conversation when today, with some of the natural language parsing that's happening. Anybody heard what is it, Google Duplex, which is pretty scary. That you can call someone, have a pseudo conversation with make a reservation, and and the other person doesn't know that they're talking to a Google Assistant. It's at some point there must be some legal issues there that where Google has to identify itself as a non-human actor, representing somebody or on behalf of someone else, right? Scary. Anyway, so SQL provides a sort of pseudo-English way of trying to interact with databases, us manually giving commands to a database, and it has a fairly simple syntax. Here's one of them, the most common one: be able to retrieve data from some set of tables. It reads as select the fields that you want from a particular set of tables. We specifically refer to this as a select clause and the from clause, and so this is kind of like the select in the relational algebra, where this is the projection, which fields you want, right, and what are the tables we're going from, right? So this is just a projection. That's it, right? We don't have the select because we're missing the predicate, right? So this is kind of filtering, grabbing all the records, right? But filtering horizontally. I only want a subset of the fields. But the select is meant to be able to combine both, right? The select plus the projection, right? Where the select takes as argument a table and a predicate, and then the projection just takes a table and then a subset of the fields that you want. But nevertheless, the select statement in SQL tries to combine both into one single syntax, and it is to filter out from a plethora of data sets, right? Many rows, many fields. Identify one single set of results that have only that subset of rows and a subset of those fields. Right? So that's the intent for SQL queries. So here's our trusty little database that we're going to be using throughout. Being able to retrieve data, presumably from a particular table called the student table, and the fields that we want. So we only want here student name and graduation year. Notice that we are putting a prefix in front of the fields that we want, specifying which fields we want from what table we want. If it's usually if we just have one table, then there's no need. It's implied that the fields we want are from that table. But if you have more than one table, then you would do the prefix it to disambiguate which fields you want. Right? So here's the equivalent relational algebra statements that we looked at earlier. Range. So oftentimes these table names are fairly cryptic or long, and so we can create aliases, right, that we can reuse inside of the select clauses, so that we can create an alias of the s dot and then the name, which is it's fairly useful if you want to be able to join, right, with a table with itself, right, that where you might call them different ways, right, so that you can say S1 and S2. Right, so you're joining your student with itself, right? And that's how you would disambiguate between the two. There's some shorthands, like for instance, One of them is it's implied. The name of the table is implied. You don't have to provide it unless you need to disambiguate. Or if you want all the tables, then you can just say star. Or if you want all the fields from one table, but not all the other ones from the other table, you can prefix it with the table alias or the table name in front of it. Here's a couple examples on a simple schema, the department and the employee schema. And notice that if the names would have been the same, right? If you're joining department and employee, and they both would have had the same field name and name, right? You would have had to disambiguate, right? You mean the name for the student, or do you mean the name for the department? Luckily here that the department has the name as opposed to name, so we don't need to disambiguate. It's understood which ones. So here it's implied that names come from employee and D name come from the department. But there's no need to disambiguate. But if they were the same, we would have to add that. Here's an example of retrieving all the fields or only the last name and first name of that particular table, person's table. If you have fields that are not unique, right? They're not primary keys that have repetitions, and you want to retrieve them. You can apply the unique keyword in front of it or distinct that filters out any repetitions. Obviously, this creates more work for the database, right? Because it has to keep track of the ones that it has already seen, right? And every time it sees a new one, right, it needs to check if it's in the list that it's keeping track of, right? So you're adding another for loop, right? Each one of these is a loop within a loop within a loop. You're just configuring with a pseudo English interface. You are configuring just lots and lots of loops that are occurring here, right? Each one of these fields is strongly typed from a plethora of distinct data types. They can be numeric, small integers, float, integers, doubles. So there's a whole bunch of numeric data types. There's a whole bunch of character and string data types as well. There's also several functions that can operate on these pieces of information, such as you can concatenate, you can parse dates, you can extract all sorts of information from different that you can use on the fly. You can convert strings into lower, uppercase, or trim them, remove any extraneous spaces, calculate the length of a string. Lots and lots of functions that you can operate on the data as it's being queried. You can search for substrings. You can access the current username, user that's currently logged in. So that, for instance, you might want to list data that is only pertaining to the person that's currently logged in. Concatenate strings. You can do pattern matching, whether it matches a particular substring or a particular pattern with single characters or multiple characters appearing multiple times. So here's an example of the like function that allows you to pattern match a word like Einstein matches a pattern, single character I followed by any number of characters I followed by a single character, and other strings that might match the same criteria, and those can be used in select statements. Here's just a syntax of the like pattern. So here's our first predicate, right? That's now looking more like our select from a relational algebra. We have the select columns. That's our projection, right? And then down below, the from and the where is more the select from the relational algebra, right? From the table, and then the where clause the predicate that we want to match. Here, the predicate is using the operator like, that is taking from every record that is iterating over. It's pattern matching that particular column name against a pattern, and that pattern can be have percent signs to match any number of characters, or underscore for matching exactly one character. And there's all sorts of other operators, not in this character list, in this character list, starting with that particular character, ending with that particular character. So there's lots of little operators within like. So here's a couple examples. retrieve all the fields from the persons table where the city starts with LO. Okay, and by default it's a case insensitive. Right, you would have to explicitly say that you want case sensitivity here, or case insensitive, so it matches only the city that started with LO, Lowell. Dates, there's several types of dates, and each vendor might have different if you're a SQL Server or Oracle, or each one will have different versions of their dates. But here are the more common ones, different formats: year, 4 numbers for the year, 2 numbers for the month, 2 numbers for the date. And there's also interval, allows you to calculate, do a lot of math arithmetic, right? That you can see the differences between 2 dates, how many days are between 2 days, 2 particular dates, or how much is it one particular date plus so many months, so many days. So it's pretty cool. You can also compute based on the current date, or easily parse and extract a particular field of a particular date, the month, the year, the day, and then do all sorts of arithmetic of adding to a particular date, adding so many months, so many days, so many years, and it'll know how to handle leap years and all sorts of calendar operations. And also do some date arithmetic on saying how many days there are between two dates. So anyway, so different vendors will have different representation, different formats, different data types. Some of them are pretty common. Date and date time is pretty common across all vendors. But then each vendor will add its own little way of representing dates. You just have to be aware of that. Later on, when we look at use JPA, we'll abstract all this, right, and just configure the database and have the JPA handle all that, right? Once you get transform it into a different data representation like Java, or you want to abstract these low-level details on how the data is being represented. All sorts of operators that are being provided by the different vendors. Here's just a few of them for retrieving the current date, being able to add dates or subtract dates, or compute the difference between 2 dates, or format the dates in all sorts of different types of different locales, military, European, using dots or dashes or slashes, or also all sorts of formats that you can configure. SQL has its own functions. Again, different vendors will have different representations. Here's just a couple of examples of extracting all sorts of dates and converting between various data types. I believe this is in SQL Server. So this is inside of SQL Server. So using some of their representations of converting it into dots, slashes, or whatnot, right? And if you want abbreviated, you want the verbose representations. Right. So the select clause, as I mentioned earlier, allows you to select the different fields that you want, and also do some on-the-fly calculation, like use to implement the extends operator in relational algebra. So here's a field that did not exist before, right? And here's one that we're giving it a name, here's what we're renaming. So this one is a rename operation. We're renaming one field as another field. Here we are calculating on the fly. We're calculating the subtraction of 2 values. The value in the record minus 1863, and we're doing a rename. Right. So again, all those operations in relational algebra, but now given this thin layer of abstraction. With the pseudo-English, but underneath, all this is converted back into a relational algebra representation, right? Because this eventually actually has to be executed, right? This the program parses your query, converts it into an actual set of operations that's going to execute, and so some of them will be select, some of them will be renamed, some of them will be projections, some of them will be products and joins and whatnot, right? And it creates this plan on how is it going to implement execute this, right? And you can actually look at the plan and what is it planning to do, right? And see if there's some optimizations that you can add to that plan. So here's apparently, okay, this is the query. Yeah, this is the query. This select statement returns something like this. Student name, the major, the graduation year. So they're all the 153rd graduating from Boston College. So here's an example of a query and with several slides that give an example of how we might transform this. So this just returns 3 fields from the student table, but then we can rename them. Right? We can rename a couple of them. The student ID, we can name it as new SID, and the grad year as grad decade. Presumably, we're going to calculate something here from the graduating year. We like to maybe divide by 10, right, or do something where we can calculate. So here we are concatenating the original student ID. We're concatenating student hash, right, and that will be our new student ID. So we are arbitrarily just calculating a new student ID. And then notice that we're now for the decade we're calculating this, right? We are dividing by 10. Basically, we're truncating, right? So if you graduated in 2001, 2002, 3, 4, all the way to 2010, right? You're in the 2000 decade, right? Or in the 2010, 2020, 2030, right? So what decade did you graduate in, right? So we're basically first dividing by 10 to drop off the last. And then we're multiplying again by 10 to drop the last integer. And we're casting it back to an integer and then displaying as the graduating decade. So here we have all these students. They all graduated in the decade of the 2000s, right? And their new student IDs is to concatenate value. You can also, as you're iterating, you can take some decisions, right, on whether to do the result be calculated depending on the value or some Boolean operator, so that perhaps you can calculate a value based on the current value if it falls within a particular range or if it falls within a particular predicate. So there's 2 syntheses. There's one of them. Where you have a case, like a switch case statement, where you can say, case when, the condition then, and then you can have all sorts of whens, lots of whens, right? That you can where you can evaluate individual conditions. So this is more like an if else, where each if has an individual predicate, right? And the value, the result, is the resulting value from that calculation. This can be embedded in each one of the in each one of the select clauses, right? So, for instance, here's an example where we are selecting the original A, but then we are adding a second field here, the second field, whose value is whatever this evaluates to, right? So if A is 1, then the second field is going to be the string 1. Instead, if A is 2, then it evaluates to 2. Otherwise, it just evaluates to other. Okay. So notice that the second field, right? It's based on the other field, and we are calculating it on the fly, right? So this value 1, 2, and other, right? We're calculating on the fly, right? Which is pretty cool. Calculating inline. There's a second syntax for the case. Where the instead of having each when have its own predicate, right? You only just have one predicate, right? That evaluates something. So you have an expression, and this evaluates to a single value, and then it's compared against any number of possibilities. This is more like a switch case, whereas this one is more like a nested if-else's, right? Lots of if-else. This is more like a switch case, right? So where you have the switch evaluates one predicate against multiple values. So the same example earlier using this new syntax. You can certainly do arithmetic operations, extract, retrieve a particular field of a particular date from the current date. We're extracting the year, and we're subtracting the year that the student graduated, right? And based on that, we can determine whether this person has yet graduated or not, right? Presumably, if it's within a particular range, then they have already graduated. So, for instance, if the current date is 2011, we extract the year, it comes out to 2011. If they graduated in 2007, then this returns that you are a graduated, you're an alumni, right? If instead the graduating year is in the future, that might give you a negative value, right? And says, well, no, you haven't graduated yet, so you're not an alumni, right? So based on that, we could have a case that calculates this, right? So give me all the alumni, right? And so this could say, or give me a list of all the students and add a column at the end that says whether they're alumni or not, right? So we can say, if the Q alumni years is greater than 0, then you're an alum. Otherwise, you're still in school, and then we're going to put that in a field called graduating status, right? Or you can use a more compact version of this, where it's just an if statement. Right? You can say if greater than 0, then alum, otherwise in school. Very much like Excel might do, right? And you might have a cell, and then you have an if statement that has three arguments, right? The predicate, and then 2 possible values, a true and a false result set. All right, so let's take a look at the original table that we're using throughout, right? And then let's use it in a couple of queries. So here we are retrieving from two tables, students and departments. So what would that be, right? So that's our product, right? That's the product operation that we looked at earlier in the algebra, right? In the relational algebra. This is looking at students and departments. Notice that it has no predicate, right? Since it has no predicate, it's going to return the cross product. It's going to consider all the possibilities between the all records in student and all records in department. Okay, because I'm not filtering. You're not telling me. Oh, only those students that are in this particular department. Since I am not filtering, you must mean all possible combinations, right? So this since we have 3 departments and 9 students, there are a total of 27 possibilities, right? So this comes back with 27 results, right? All possible combinations of Joe with computer science, and Joe with math, and Joe with drama, right? Those are 3. And then Amy with computer science, and then Amy with math, and then Amy with drama. There's another 3, right? And if you go all the way through, it's 9 times 3, it's 27, right? So that's what we meant by the cross product, right? So this is it. There's our cross product. Typically, this is useless to us. We would never actually do this. Instead, we would either use an actual join and says, well, no, I don't care about all of them. I only care the ones that meet a particular criteria, right? And so you give it some predicate. Here we haven't, so you end up with all possibilities. So here's a self join, right? Where here we're doing a cross product of the student table with itself, right? So it's 9 times 9, so it comes out to be 81 possibilities, right? So it's Joe with Joe, Joe with Amy, Joe with Alan, Joe with all the other ones. Then they go back Amy with Joe, Amy with Alan, Amy with blah, 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 everybody, right? So you come up with, 9 times 9 comes out to be 81 possibilities. But here, to be able to disambiguate between which name are you grabbing from what table, right? We give them different names, right? So student S1 and student S2. So you can grab some names from one of the tables and a name from another table, right? So that's so here we have to disambiguate. You have to give them names. Combining tables. So typically we won't do this, right? We won't actually use a cross product, right? It's just useless to us. More commonly, we will apply within a join, right? Where we do have where we are going to be able, we want to filter out, right, and only keep those that make sense, right? Where there's some kind of relationship, where, for instance, a particular student might be associated with a particular department, right? And so we use the join operator between two particular tables, and then a predicate that we're going to filter, right? So, but nevertheless, we still have to iterate. So the way, if you think about it, this is basically the database in the most naive implementation, right? We start at Joe, iterate over the entire table of the department until it finds the correct department, right? And once it finds it, found it. Right? Worst case, it's the last department. Yes? And then once it's done with the first student, it's going to go to the second student. And again, it's going to iterate over the entire department table, right, until it matches. And then it go on to the next student, and then it's going to iterate over the entire table. So basically, it's full scanning the student table, and for each one of those, it's full scanning the other table, right? So basically, you have a quadratic complexity, right? You have a linear search on one of them, but for each one of them, you're doing a linear search on the other one. Yes? So it's quadratic. Imagine if you're joining 3 tables now, right? If you're joining 3 tables, then it would be, for every record of these, you're iterating for all through the records for the other table. For every record of these, you have to iterate over the records of the other table. See that? So you're doing a 3-way loop, right? A loop within a loop within a loop. Okay. So you want to try avoid as much as possible. These joins are very expensive, but we'll see how they can be optimized. So we're joining the two. So we're iterating over the student table, we're iterating over the department table, and we only really care about these over here. But nevertheless, worst case scenario, we have to, full scan one table and full scan the other table, the cross product. So returns the names of the major departments. Now there are a couple of types of joins, like we mentioned earlier, the semi-join, the anti-join, right? We looked at some of those joins, and they have specific names here as well. Here we have the inner joins, the left joins. So those are the different types. The inner join is the most common one, right? Where we have some unique identifier referring to some other identifier, where you have a foreign key matching a particular primary key. Those are the most common ones, right? Where we want the records of one of the buckets matched with some records of the other bucket. So that's the more common one. We call it the inner join. But we certainly have the other one, right? The left outer join, the right outer join, the ones that I want to know which ones match, but now also from the ones that didn't match, right? I want the ones from a particular subset, right? For instance, the example I gave earlier about spouses and faculty, right? And you might have a table of faculty and a table of spouses, and even the ones that don't match, I still want the faculty, even if they don't have spouses. So left and right joins allows us to do those kinds of questions, retrieve data from tables that even don't match. Full outer joins is, I just want all of them, right? So give me the ones that match, but then give me the ones from one and the other that also don't match. It's just returning. That typically we don't use. All right, so typically the syntax is that you have the column names that you want, the 2 tables in question, and then a predicate that how you want to filter this out. Here's an example of just a plain old inner join, where you have here some orders and some persons, and then we're joining the 2. And notice that the orders have references back to the person. So we have 3 people here, and we have the person IDs are referring to Bob, Charlie, and Dan. Notice that nobody's referencing Bob, and here we're referencing somebody that doesn't exist, right? So typically this would not be allowed, right? We say that this is breaking referential integrity, right? So it's referencing some record that doesn't exist, right? It's okay that nobody's referencing Bob Dole. Nobody would ever reference Bob Dole. But this typically would not be allowed, right? If this were a foreign key to a record that doesn't exist. I don't know how we ever got into that perhaps we weren't having those constraints, right? So using that example, let's use a couple of joins where we're retrieving the last, first, and order number. So the last and first we're grabbing from the person, and the order number from the orders, and the predicate is that they match. So there we go. So we have Boone and Garcia, and we have the first and the order number. So that's the most common inner joins, right? But let's look at the other ones, the ones that are left joins. That this says, yes, give me the ones that match, but for some reason I might also want the folks or people that don't match, or I might want the orders that don't match. Okay, and that's where the left and the right comes from, right? If the person is on my left, then I want the person, and then I want a left join, right? Or if I want the orders, even the ones that don't match, and that's to my right, then I would do a right join, right? It's from the so this says table left join table 2 says so certainly do the query, but if there are any left over from table 1 that don't match, I want them to. Bring them over, right? Even if they don't match. Or I might do a right join. It says, okay, do the join normally, but if there are lingering records on the table to my right that don't match, bring them to, right? So for instance, an example might be that notice that here we have orders. We have a couple that don't match here, right? That's on purpose. We have 1, 3, and 15 that we don't have any 2s here. And on that side, we have 1, 2, and 3, but they don't match with the 15 over there, right? So let's do a left join. Notice that on persons, notice that we have the original query that we had earlier, right? The ones that match, but there was a lingering record on the left on the persons that didn't match anybody on the orders, right? But here we want to display also that person. It might be retrieve to me all the folks that have an order, right? Because I want their order, right? But I might ask if any, right? So that if any, right, tells me that okay, so you want a left outer join or a right outer join, right? If it would be just retrieve me all the folks that have an order, right, there would be a plain old just inner join, right? But if I say if any, right, so that's a clue that says, oh, wait a minute, you want also the ones that don't match, okay? So outer joins. Oh, okay. So here's the example. Here's I have the spouse, you have the staff, you have 2 tables, and you have social security numbers and the spouse social security number. And this is referencing the ESSN, right? It's referencing the staff. Okay, and so the query might be, find the name of each staff member and his or her spouse, if any, right? So I want both names of all the staff members and their spouse. So that's where I have the inner join would only retrieve the staffs that actually have a spouse, right? Would not retrieve the ones that don't have a spouse. But the if any gives me an idea that wait a minute, I also want the staff that don't have any spouses, right? Right join is just basically the other way around, right? That you want the information that's on the right hand side. So let's look at the same example here. Notice that we have all the orders and folks that match, but there were some lingering orders that didn't match anyone on the left hand side, but we want those too, right? Well, obviously, if you switch the tables around, right, then the meaning changes, right? So basically, the left and right means something to you, right? Where you place your tables. Full joins just returns when there's a match in either of the tables. So when there's a match in either table, then they come back. So for instance, in our example, we would return the ones that match, right? For all of them, plus all the records that don't match from either one. So it's like it's a left and a right, I guess, right? The ones that don't match for either one. Now, if you want to join more than one table, you can certainly do that. You can combine them using maybe parentheses or you can just string them together one after another. and they would be interpreted in sets, right? In sets of two. So you first would do a particular join between these two tables, and then result of that would be then joined with some other table using a different predicate, right? Each join will have two tables, right, or two data sets with its own predicate, right, and then joined with another data set with its own predicate, right? Now this could become fairly hard to read, if you have lots and lots of these joins, especially understanding that right there it's cubic complexity, right? So you have three nested loops iterating over the three different tables, right? Student, you're iterating over the student, for each student iterating over the enrollments. For each of the enrollments, it's iterating then on the section, right? So that's very expensive. Now there's an alternative syntax that can be used where you move the predicates to the where clause, all right, as opposed to leaving it in the join. Now we refer to the when we put the predicate in the join proper, right? We refer to that as an explicit join, right? I'm explicitly telling the database that I want a join, whereas this one is not explicit. We say that it's an implicit join notation, right? The database might certainly convert this, right, into a join proper, right? Because basically that's what it is, right? A join is just a predicate inside. It's applied to a cross product. But this predicate is more common, right? It's a little bit easier to read, right? Although sometimes it's cumbersome when you have predicates that are used for the join combined with other predicates that are not used for the join, right? That might be operating on fields that are not primary keys or foreign keys, right? Just maybe applying on the salary or the birth date or something that has nothing to do with joining the tables, right? All your folks that have been with the company so many years or whatever, right? Those are not predicates that join the two. So oftentimes folks will stick to leaving the joins, especially if it's just two tables, right? That's easy to read. They'll keep the explicit notation, but then leave the where clause only for the non-key, non-primary key or foreign key fields. The where clause. The where clause is what allows us to filter and provides a predicate to filter the values in the query. There's lots of operators that you can use on the where clause to compare to build your Boolean expressions, right, that match your predicate. Certainly there's the equal operators, the not equal, less than, greater than, whatnot, between, like, in. Obviously combined with ands and ors and, to make an arbitrarily complex Boolean operator. Just keep in mind that Boolean operator is going to be executed, in every single combination in the tables that you're joining. Right. So here's a pretty simple example on retrieving all the persons whose city is Lowell. Here's an and with last name and first name, returning Bob Dole. Here's an or with Dan or Bob, returning these two. Here's an and or combined with the parentheses, right, to combine a Boolean operator. These are all pretty simple. Multiple joins, where multiple joins are okay. Yeah, so they're easier to read. Right, they're easier to read in the implicit join operation as opposed to the explicit operation, right? So this is such much easier to read. Now a lot of the queries are used here for non-field, non-key queries most of the times, but you can certainly use them to write simpler ways of navigating from one table to the next. Here, notice we're implementing the join above. We're implementing it with an implicit join down below. We're navigating from the student to the section to the enrollment. Right, we're navigating from between three tables. right? Here from the student to the enrollment, and then from enrollment to the section, right? And on our way, we're grabbing some of the information. We're grabbing the student name. We're grabbing the professor name. Notice that the only way we can grab the professor is to go all the way down to the section, right? So yeah, we're using the enrollment as a means to navigate down to the section. We're not actually grabbing any data from the enrollment, right? Like the grade you got, right? Joins. So here's a combination of using both. We're using some of them are being used for join, right? And with a combination of some of them that are not part of the join, right? So here's where it gets a little bit hard to read, where some of them are being used for navigating between the tables, and some of them are being used just to filter. Right? I only want the ones that whose section or student name is Joe, or it was offered in a particular year, right? Here's the between operator, right? That allows us to consider ranges of dates, ranges of numbers, or also alphabetical, whether you're in a particular range of strings. So here's, for instance, we're saying, return to me all the folks that are between Boone and Garcia, right? So this is in string order, right? In alphabetical order. Not between kind of goes the other way around, right? So the one that don't match. So you can always put a not in front of any predicate, right, to negate it. In is also very useful. That allows you to take the name of the value of a field and just compare it against a enumerated data type, right? So in the in you can have multiple values, and that value will be compared against any one of those, right? And the first one that matches then makes the predicate true. Again, this is expensive, right? Because it has to iterate over the list. So that's linear search. So it's linearly searching through all the values, comparing that column name, right, compared against each one of those values. So makes it expensive. So here's retrieve to me all the records whose last name is in Boone or Garcia. So it's going to iterate and compare last name with each one of these and see which one matches. Some other operators like an extract, like we saw earlier, right? That does a pattern match against a string, pattern, and extract the you can extract the year, right? And then compare it against a particular graduating year. So current date, for instance, you can calculate. So who's graduating this year, right? Current user keeps track of the currently person who's logged in, right? The username of the person who's logged in. So this would allow you to, if you have multiple faculty using the database, they might want to see only the data that pertains to them, right? The sections that they're teaching, right? The students that they're teaching, or the section that they've taught in the past. So they could use current user to filter that out. Some constraints allow you to ask the database to validate certain things about the data, that whether something must be null, not null, whether it's unique, whether it's a primary key, or to enforce certain behaviors, right? That this field needs to be unique, meaning that make sure that out of all the records, for every record, all those fields need to be unique. Even if they're not a primary key and foreign key provides additional constraints. Constraints means that whenever a record is being created or is being modified, the database will enforce certain rules, right? So, for instance, if you're trying to insert something into a database and a field has been declared unique, it will, before it accepts inserting into a database, it will look at that field, bless you, and it will go through the entire. It will scan the table, right, to see if that particular field is repeated anywhere in the table. And if it finds that it's already taken, then it won't let you insert it, right? Ideally, it won't actually scan. Typically, it'll have all these trees, all these B trees that we're going to look at later on. to quickly determine whether this key is already taken, right? Instead of having to scan the entire table, right? We want to avoid linear search as much as possible. Primary and foreign key add additional constraints. Primary key, not only does it have to be unique, so primary key implies that it's unique, right? Meaning that it's a unique identifier, but it's also meant that it's participating in some kind of relationship, right? That some other record might be referencing you, right? So that since you now the parent, then you cannot be removed because there might be other records referencing you, and if you're gone, then there's going to be a whole bunch of other records that might be left orphans, right? So yeah, primary keys and foreign keys allow you to add these kinds of constraints, right? So that if you try to remove something or insert something, maybe if you try to insert a record with a foreign key that doesn't match any primary key, right? It would stop you and say, no, there's no, you can't be the child of someone who doesn't exist, right? So again, all these constraints are so that the database helps you keeping the data valid, that it's not, you're not inserting bad data. Check is more of a generic check. You can give it a predicate, to check that when you insert, you can't insert somebody with a negative salary or something, or negative or date of birth in the 1800s or something. I don't know. Or you can add specific constraints, right? Generic constraints of a particular record. So here's an example of using the create statement that allows you to create new schemas, create a new table, and set certain constraints. The most obvious constraints are data types, right? That you say that last names need to be strings, and this needs to be a date, and this needs to be an integer. All right, those are constraints, right? Every time you insert or you update, the database is going to stop you if you don't follow those constraints. Some of them, for instance, here .null, meaning that that is a required field. The other ones are okay if they're null, right? It's okay if you don't give me the first name, address, and city, but you have to give me last name, and you have to give me a unique identifier, the primary key. So here's an additional constraint saying that PID it's required, and it cannot repeat, right? So that when you insert, before it allows you to insert, it'll check that value against all the other values in the database, right? And make sure that it's not repeated. Typically, when you add the constraint primary key, it automatically adds the other constraints, unique and not null, right? That's kind of implied, right? Now the constraints, any additional constraints, typically you can name the constraints. You can give them names. So by default you can just give unique, right? But you can name the constraints, giving them a unique identifier. Typically that's very useful if you intend to alter those constraints at a later time, so you can refer to them by name. Otherwise you would not be able to refer to it, right? So naming the constraints is useful, but it's not required. Most databases, if they are creating the schema, they will create a constraint name, right? Now in the assignment, I believe I asked you to follow a naming convention for some of the constraints. So please follow those naming conventions using the constraint keyword. So here's a primary key constraint. Again, this is asking the database to please validate, right, relational integrity, right? If these are going to, if two records are going to be referring to one another, make sure that they're valid, that the primary key exists, and that I can remove the record that has a primary key if I have children referring to that parent. And different vendors will have different syntax for establishing some of these constraints. So you'll have to use whatever dialect you're using for whatever vendor. So MySQL puts the primary key down at the bottom, whereas SQL Server and Oracle might put it right next to the field, right? And when we get to JPA, we'll notice that we're going to automate all this SQL communication. We won't do it manually. We'll instead delegate this to a library to do this, right? But we'll have to specify what dialect do you want me to talk to, right? So if it's MySQL, you'll need to tell me I want to use MySQL version 5 dialects, right? Or Oracle or SQL Server, right? So that because there are differences between the different vendors, different versions. Foreign key. This is a syntax where that allows you to declare the constraint that a particular field is a foreign key. That you might have a local field. Notice that it's not unique because multiple records might be referring to the same primary key. That's a one-to-many relationship, right? And where here you have a foreign key PID that is referring to another field in some other table, right? Meaning the value here, the value of this field PID must be one of the values from that other field in that record, in that other table, right? If I try to put here a value that doesn't exist in the other table, the database will stop me. It says, no, you're not referring to anybody. Record 15 doesn't exist. I only have all the way to 13, right? Again, a foreign key, the syntax is slightly different between MySQL and a SQL Server. Here we have a named foreign key. It's common practice to put an FK in front of the foreign key constraint just to identify that it is indeed a foreign key. This is if so your primary keys, you might have a combined primary key and you can reference combined primary keys using a combined foreign key, and then you might have two columns, right, that are referring to the other field, to the other table. You also have default, where it allows you to provide a default value for a field using the default key. So here, city, we're assuming that everyone's from Lowell. Or dates, get date, you can retrieve the current date, right, and use that as a default value for when this was created. It's nice, like, for time stamping and knowing when a particular document was created or when it was updated. SQL Autoincrement, this is a very convenient feature that allows you to delegate the generation of the primary key to a database if you don't want to have to deal with that. You can generate them yourself, or you can delegate it to a database. So every time a new record is added, you just take the next available unique identifier and use that for my primary key. Again, in MySQL, it's Autoincrement. In SQL Server, it's identity. So if you declare a field to be an Autoincrement, then when you insert, it's that field is not required. You don't have to give it to me, right? Because I'm going to generate it, and if you give it to me, I'm going to ignore it, okay? Because I'm creating it myself. So you can provide null or just let it go, right? Just not even provide it at all. Vars. Unfortunately, in Oracle, it's you don't have the equivalent. You have to create a sequence that you have to then pull the next available value from. So you can create a sequence that gets incremented by 1, by 10, and whatnot, and then pull from that next value. All right.